detect construction elements automatically from construction job sites from digital images to help progress reporting and updating the schedule by accessing to as-built information. Unfortunately, there is not open and public data set from construction job sites to train these deep learning algorithms. Hence, many researchers utilize 3D BIM models to extract synthetic images to create digital image datasets for training these deep learning algorithms. Object detection and recognition has two approaches. One of them is traditional or feature-based algorithms, and the second one is deep learning algorithms which provide us with more practical solution in the construction industry. They have promising performances and have higher accuracy, and also because they have self-learning capabilities. Many researchers in the construction industry utilize these deep learning algorithms to detect the structural and building components such as beams, columns, walls, doors, and other components. And some of them integrate this technology with other technologies such as BIM and virtual reality. Our research objective is developing a method for timely recognition of installed HVAC ducts utilizing synthetic images for automated progress reporting. For this purpose, 3D BIM models were used for creating image dataset. A deep learning algorithm for automated identification of HVAC ducts were utilized, and transfer learning and data augmentation technique for improving the model performance were applied. Our methods include three main modules. The first one is synthetic image generation and data labeling. The second one is mass Gaussian and training. And third one is testing and evaluation. In the first model, 3D BIM models are used for generating synthetic images. Different viewpoints with different illumination and occlusions are rendered using Enscape plugin in the Revit software. The dataset class is HVAC duct, and the training dataset includes 1,143 synthetic images. Through this training dataset, we have 1,887 duct instances. The dataset distribution shows that from 1,143 images, we have 56% one duct in each images, 32% two ducts in each images, 9% three ducts, 2% four ducts, 1% five ducts. After creating the dataset, we used via web tool to annotate our images to create the JSON file for training our deep learning algorithm. In the second module, the mass Gaussian, which is an instance segmentation technique, has been employed. The convolutional backbone network were used to extract feature maps from an image. And then these feature maps fed into region proposal network to propose the regions of interest. In the head network, fully connected layers perform object classification, bounding box regression in parallel with predicting masks. Pre-trained weights on the MS COCO dataset are utilized for transfer learning, and different sets of data augmentation techniques such as flip, rotation, brightness, and Gaussian blur were applied to minimize the overfitting problem and improve the generalization of the model. The result of this image augmentation can be seen in this image. Precision, recall, and mean average precision were used to evaluate the model performance. 172 images are randomly selected for testing and validation purposes. To assess the effect of augmentation technique on the model performance and HVAC duct detection, Two experiments are conducted. In the first experiment, data augmentation is not applied during the training process, but in experiment 2, data augmentation technique used in training process. And according to the results, we can see that the application of data augmentation technique is meaningful and helpful for training our model because the precision achieved 80.87% with recall of 87.84% and mean average precision score of 90.6%. Also, the training loss and validation loss of the experiment 2 shows that we do not face overfitting problem and shows that the model performed well. The model is implemented in Google Colab Pro, which is a cloud service based on Jupyter Notebooks and Python. And the model training time took 4 to 5 hours. The results of this model is shown in this picture. And it shows the detected HVAC ducts that have very specific shapes. The main contribution of this research is development of a solution to automate HVAC ducts recognition for automated progress reporting, making use of as-planned and as-built stages via digital imaging taken from either 3D models or real construction job sites, and also utilizing synthetic images that are generated from 3D BIM models to train a deep learning model for HVAC duct recognition due to the absence of an open image dataset. To increase the model performance, transfer learning based on the COCO dataset, and different data augmentation techniques were applied. The developed method advantages are providing a robust and accurate tool for recognition of installed HVAC ducts, automatically utilizing synthetic images, and also reducing the manual effort and time in monitoring and reporting process. In future work, a larger training set, including a mix of both synthetic and real images, is going to be evaluated. Also, impact of other augmentation techniques is going to be investigated. The developed method can be extended to detect additional building elements such as piping, beams, among others, to help progress reporting to be more efficient. And also performance of other deep learning algorithms can be investigated. Thank you so much for your attention.